I wanted to record an extra bonus video where we talk through the formula for the line integral of a scalar field and talk specifically about why this formula works. Now, to help us to get some physical intuition, we are going to situate ourselves in a physical context. And specifically, I'm going to go back to when we were talking about calculating mass from density. Back when we were dealing with one-dimensional straight objects, the object had a linear density function. A linear density function, rho of x, which was a function of a single position variable. Because if your object was straight, and if your object was basically one-dimensional, every single position on that object could be described just using a single input variable x. Now, when our linear density function was a function of one input variable, in that situation, we saw that the method for finding the mass was to integrate a single integral of that density function with respect to x. And that came from the fact that if you take a small portion of your object that had a length of delta x, then the mass of this little piece of the object was approximately equal to the density as measured at some location within that piece times the length of that piece. Linear density times length was approximately equal to the mass in this little chunk of your object. And then if you added together all of those masses of all of those little pieces, that was approximately equal to the object's total mass. Now, that approximation was bad if your pieces were very large, because if your pieces were very large, then the density within that piece could vary greatly. So just picking a random density at one location within the piece was not very representative of what that whole chunk was doing. But if we let delta x shrink to 0, and if we let the pieces become very, very small, then this Riemann sum estimate for the mass becomes a perfect definite integral that can be used to perfectly calculate the mass. So from this example, here is what I want to highlight. I want to highlight that we found the mass of each piece by taking the density at a certain point within the piece and multiplying it by the piece's length. When we did this, then we just had to apply a sigma and then apply a limit that allowed the piece to get smaller and smaller, and that gave us the total mass perfectly calculated by way of an integral. So now let's cut back to line integrals of scalar fields. When you are deploying a line integral, you are typically dealing with an object that is essentially one-dimensional, like a rope or a wire, but the object is not straight. It's been bent somehow and curved to occupy two-dimensional space or three-dimensional space instead of just one-dimensional straight line. So this means that positions along the object have to be identified using two coordinates, x and y. And the density of that object at that position must be a function of two variables. The positions along the object must be expressed using two coordinates. So the linear density function is a two-input function. Now let's go ahead And let's parameterize this curve. So I'm going to let r of t be a parameterization for my bent curve, my bent rope or wire. If I parameterize the curve formed by my rope or wire by this function r of t, and if I think about the vector r prime of t, do we remember what the vector r prime of t represents for a parameterized curve? The vector r prime of t represents a tangent vector to the curve, right? So potentially a vector that looks something like this. Now, depending on your parameterization, this tangent vector can end up being quite long, and the longer the tangent vector is, the more it tends to deviate from the trajectory of the curve itself. If you have a very, very small tangent vector, however, a very short tangent vector, it tends to hug very, very closely to the arc of the curve. So what I'm going to do in order to shrink this tangent vector and make it smaller is I'm going to scale it and I'm going to multiply it by a small change in t. And this small delta t applied to the tangent vector will shrink the tangent vector so that it hugs pretty closely to the curve. Now, if I wanted to determine the length of this shrunken tangent vector that I have just drawn, I can do that by taking the magnitude of r prime and multiplying that by this scaling factor delta t. Magnitude of r prime times the scaling factor delta t. The delta t is already a scalar, so when you're finding length, you don't have to change that in any way. Okay, so here is our curve C representing the rope or the wire that we are dealing with. The vector r prime was tangent to the curve C, and so if we made that vector shorter, that vector would be a very close approximation to what the curve is doing. And so the length of this tiny shrunken tangent vector would be very close to the length of this little piece of my rope or wire. Okay, so now we have found an expression that very closely approximates lengths of little pieces of the rope or the wire. So now I'm going to use that to help me to find the mass of this little segment. Mass of one piece of rope is approximately equal to the density as measured at some location in the piece times the length of the piece. Now, the density, as measured in some location within this piece of rope, is given by the density function as evaluated as a specific position in that piece. And the length we just found, the length of that piece, was approximately equal to the magnitude of r prime of t dt. So if this expression gives the mass of a single piece of rope, then to find the total mass of the rope, all I need to do is add together all the masses of all these tiny pieces. So I can do that by applying a summation to this expression density times length. And therefore, if I want to take this Riemann sum approximation for the total mass, and I want to turn it into a perfect integral to calculate the total mass, all I have to do is shrink the delta t so small that it becomes a dt. Now, what we have drawn right now, what we have written so far is correct, but it's not completely useful in its current format because this is an integral with respect to t, but my expression still contains my other variables, x and y. And in order to make it possible to calculate an integral, you want as much consistency in the variables that you're using as possible. And so that's where the parameterization comes in. The parameterization gives us a way to replace x and y with the formulas in terms of t instead. And so to represent that, I'll say plug your parameterization into the density function. Wherever there was an x, replace that with the x given by the parameterization. Wherever there was a y, replace that with the y given by the parameterization. That way your entire problem here is in terms of just a single consistent variable, t. And this integral would allow us to calculate the mass of a bent one-dimensional object, such as a bent wire or a curved rope. And we can see that what we have obtained here by studying this physical example is an exact match to the formula that we use to calculate line integrals of scalar fields. This expression absolute value, this magnitude of the tangent vector multiplied by dt, is capturing a little tiny length of the curve C that is forming our region of integration in this problem. And so we are essentially adding up outputs of our function for different lengths, little tiny lengths of the curve C. And that is what's happening in this formula for the line integral of a scalar field.